All right, so welcome everyone to the API crash course. We call the course Leveraging RCSB PDB APIs for Bioinformatics Analysis and Machine Learning. This is a part of a series of courses organized by the Rutgers Institute of Quantitative Medicine and by the RCSB Protein Data Bank organization. And there's been recent courses, for instance, one in PDBx, mmCIF in May 2023, and we had previously a course on the integration on computer structure models in the RCSB.org website. Today we're going to be talking about APIs. We're hoping that we are going to do other courses on APIs later next year. So just watch this space. And so just want to introduce myself also. I'm Jose Duarte. I work as a scientific software developer at the UC San Diego site of the RCSB Protein Data Bank, and I'm also the site manager for this site. And so with that, I'm going to get started with some explaining how the course will work. Just want to say that we have 300 registered people, and right now I'm seeing 134 online. So thank you everyone for coming. We are splitting this course into two parts. The part one is the one we are going to do today. That will be 2 hours in total. We are going to be introducing the APIs, sort of the theory of everything. We're going to tell everyone how the APIs work, mostly the search API and the data API, and showing a few examples, etc. And then we will have part 2, and that will happen over the 2 weeks after this one, on Thursdays. So October 19 will be 16 UTC. So we have, it's the same content. We are going to do a hands-on exercise with the same content, but on 2 different time slots. This is to give opportunity for everyone around the world to join. So the first slot, October 19, will be more appropriate for people in the Americas, Europe, Middle East, Africa. Second slot will be more appropriate for people in Asia, Australia, Oceania. Beware that this, for me, that I'm in the west coast of the US, this is the 26th of October, so that's 5 p.m. on the 26th of October, but that will be actually Friday morning on the 27th of October for people in Asia. So just please do be sure that you see what's your time zone, what's the time in your time zone. And the registration for the second part will be open at the end of this, will be open for all the participants of this one at the end of this session, this part. Okay, so some other logistics. We are going to be recording this, and the recording will be posted on RCSB PDB's YouTube channel, and we will also we shared as soon as possible with everyone who participated today, and with people who have asked, who couldn't make it and have asked explicitly for that, because yeah, to get to the second part is really a requirement to have gone through this first part. The presentations in PDF will be available to participants by the exit survey. We have a Google Doc for questions that will be posted in the chat also. So we'll be moderating the questions through that Google Doc. And the part 2 registration will be shared with today's participants at the end too. Okay, so I want to mention who's going to be teaching today. So myself, Rinda Balad, Diana Rose, Dennis Peel will be speaking today. And then we have Sebastian and Joan doing moderation, and they will be answering questions too. On the second part, they will also be doing the hands-on exercise, Sebastian, Joan, and Dennis. So agenda for today. We're going to start in about 3 minutes with the introduction to the APIs and data schemas. That will be Brinda Palat. I'm having the times here in my time zone here in the Pacific West Coast of the US. But yeah, and there's also the time zones in the East Coast of the US. We have the session on data API that I will do myself. We'll have a little break of 10 minutes. Search API will be introduced by Jana Rose. And the last session, a bit shorter, is a hands-on teaser on both search and data API that Dennis Peel will be doing. That's for part one. I just want to say more or less how part two will work. That will be the other two sessions, the other 2 Thursdays, following Thursdays. We'll have an introduction by Dennis, and then we'll have a walkthrough of a worked example in using Google Colab. That will be Joan and Sebastian. And then we'll also give time to participants to work on their own problem. And that's something we will ask for in the registration for part two. We will ask people if they have a specific problem they are interested in solving with the APIs. And we really would like to hear in that registration, what's your problem? So we can understand if that's something that's doable or we can help in that during those sessions. And yeah, the rest of the session will be more like time for questions, breakout rooms if necessary with the tutors, and some closing remarks. So the important thing is also to say that this is going to be limited in numbers. So because of the format of this session. So yeah, so that's about it for the presentation now, for the introduction. Here's the agenda. I think I can pass now the word to Brinda, who's going to be doing the first session. All right, I'll stop my screen share.
Yep, thank you, Jose. Let me share my presentation. All right.
Brenda, we're seeing your presentation mode.
Oh. Maybe it's because it's on the... How about now?
That's perfect.
Okay. Thank you, Dennis. Welcome, everyone. I am Brinda Valat. I am a scientific software developer at RCSB PDB. I mainly work on backend projects dealing with data modeling and all kinds of data wrangling to support the data processing pipeline and workflows at RCSB PDB. I'm happy to start this webinar, the first session, with the introduction to RCSB PDB APIs and data schema. So the rcsb.org web portal provides tools for searching, accessing, visualizing, analyzing, and downloading the contents of the PDB archive. rcsb.org provides open access to over 210,000 experimental structures of macromolecules that are in the PDB archive, along with over 1 million computed structure models predicted using machine learning methods that have been integrated from AlphaFold DB and Model Archive. rcsb.org is a living data resource where information is integrated with the PDB data is integrated with information from external resources to comprehensively deliver structural biology data to users worldwide. We also have the PDB 101 portal, which provides educational resources and training material. So before we delve into the details of the APIs or the data schema, I want to start from the fundamental concepts, the data in the PDB archive. PDB archive consists of experimentally determined structures of macromolecules and their complexes with other macromolecules and small molecules. So the data consists of atomic coordinates, the models, molecular descriptions like information about the polymers and non-polymers, reference sequence information, chemical reference information, source organisms, details about sample, experiment, and other metadata like citation, author, software. This is not a comprehensive list. I'm just giving you a broad overview of the different kinds of information that you get from the PDB. Where does this data come from? It's typically collected from authors during the deposition process. And there's also information that's generated by software. An important value addition provided by the PDB archive is that the data is well curated. There is a curation process that ensures that the data is standardized and complete and compliant with the policies, archival policies and standards of the PDB. And we also have validation metrics for assessing structure quality based on recommendations from the community. So how is the PDB data organized? Intuitively, the data can be considered as a molecular hierarchy, as shown here. A structure is considered an entry. For example, the structure of hemoglobin shown here is an entry. The entry can consist of multiple polymeric entities. In this case, it can be it is the alpha and the beta subunit of hemoglobin. And you can have multiple copies that we refer to as entity instance. It's multiple copies of an entity, also referred to as chains. You have the quaternary structure or the assembly shown here. And you also have non-polymeric entities or chemical components like the heme molecule. So there is a macromolecular hierarchy as shown here. An entry can have multiple assemblies. The assembly can consist of multiple copies of polymeric and non-polymeric entities. So the data itself can be mapped into this molecular hierarchy. For example, data like the information regarding the title of the entry or authors belongs at the entry level. There is information at the entity level, for example, the type of polymeric entity, whether it's a protein, DNA, RNA, that belongs at the entity level. Data at the entity instance level, such as structural connectivity or secondary structure information, that is mapped to the entity instance level. And you have information at the assembly level, for example, transformations required to generate the biological assembly, that's at the assembly level. And finally, data at the chemical component level, such as chemical formula or chemical descriptors. So in addition to data from the PDB archive, RCSB.org also delivers annotations integrated from external resources. So this slide shows two tables here summarizing the type of data and the resources from which the data come from and how they are integrated into RCSB.org. You have protein domain classification information from SCOP and CAT, for example. You have molecular and function annotation from Go, or protein family information from PFAM. There are different kinds of information. And you can see that even here, just like the PDB data, this information can be mapped onto the different levels of molecular hierarchy. For example, small molecule related information belongs to the chemical component level. Protein domain classification belongs to the entity instance level. citation information belongs to the entry level, and so on. So the data from the PDB archive and everything that is integrated can be mapped on to the molecular hierarchy. So once this integration happens, the data is populated into a data warehouse and delivered through an API, which powers the RCSB.org web portal. So the portal is powered by not just by the data API, but it's powered by APIs in general. And the good news is these APIs are available for public consumption and can be used by external resources to programmatically access the data that powers RCSB.org. So the goal of this webinar is to introduce the APIs that are available and enable users to understand how to programmatically access this data and use that in your bioinformatic research applications or any workflows that you have where structural biology data is applied. So there are two main APIs that power RCSB.org. The data API serves to retrieve data when PDB identifiers are known. For example, in the hemoglobin case, if you know that the identifier is for HHB, you can use the data API to get all information relevant to that identifier. And there's the search API that serves to find out what identifiers match specific search conditions. These are not the only APIs. There are other APIs. We have the model server API that provides subsets of macromolecular model data, volume server for accessing subsets of volumetric data, and 1D coordinate server that compiles alignments between structure and sequence databases and integrates positional features from multiple resources. But for the purpose of this webinar, we're going to mainly focus on the search and data APIs. But if you want more information, you can about the other APIs, you can find that on our website. So I want to give an overview of what these APIs actually power. What do they do? How you access this on the website, so then you know how you can access these programmatically outside of the website. So typically when you go to the RCSB.org website, you might use the basic search or the advanced search functionality. That's usually the starting point. And let's say you execute an attribute search, you get a set of results. What does that, and this is the search results page, and how is this obtained? The search API retrieves the identifiers matching the search criteria in the query. And then based on that, the data API is used to fetch data related to these identifiers that are then presented here on the search results page. So this additional information, like that you see here, like titles, authors, method, etc., all that is coming from the data API. And then let's say you click on one of the search results, it'll take you to the structure summary page where you can find even more information. You saw a little snippet in the search results page where you can find more information that is also actually retrieved using the data API and presented on the website. And if you go to the experiment tab, you have information about the experiment, and that's coming also from the PDB archive data, and that is also retrieved from the data API. The annotations tab gives you all the external annotations that have been integrated for that particular entry. And in this case, this example, you can see information from SCOP, CAT, etc. And these annotations are also retrieved using the data API and presented on the website. Another cool feature that you may have explored on RCSB.org is the protein feature view, or the 1D 3D protein feature view, where you can find annotations mapped to the positional features. That is, for example, in this case, you have hemoglobin chain A, you see the sequence, and then you have annotations that are mapped to these positions. For example, you have Ramachandran outliers, you have binding site information, modified residue, or cath domain description. All this can be mapped to the positional features, and that information that is also that you see on these protein feature view is also retrieved from using RCSB.org APIs. So with that introduction to how RCSB.org is powered by APIs, I want to move on to introducing the data schema, which is the foundation of these APIs and supports both the search and data APIs. What is schema? Schema is metadata. It provides information about how data is structured. In the context of databases, it's also known as data schema or data model, and it provides organization, structure, and architecture for a database. It describes how different data tables or objects relate to one another, and is applicable to both relational and document-oriented databases. You can also talk about schema in the context of APIs, which will describe how to interact with APIs. But for the sake of this talk, that's not relevant. We're going to focus primarily on the data schema. So the RCSB.org data schema follows the PDBx mmCIF data dictionary, which is the data standard followed by the PDB archive. It contains definitions for molecular structures and associated metadata that I described earlier. All those are defined in the dictionary. The dictionary is based on a custom dictionary definition language that supports the typical specifications for describing data, such as data types, control vocabularies, mandatory attributes, etc. PDBx mmCIF is designed to be extensible and has extensive software support. If you would like to learn more about PDBx mmCIF, like Jose mentioned, there was a virtual crash course held earlier this year by the RCSB PDB biocuration team. And you can find all the material from that crash course on the PDB 101 site. I encourage you to go and look at it to learn more about PDBx mmCIF. So in addition to data coming from the PDB archive in PDBx mmCIF format, the RCSB data schema also has an extension, RCSB extension, with additional definitions, which are specific for RCSB.org data delivery. And these include definitions for the annotations integrated from external resources. And in the data schema, these objects are prefixed with the term RCSB underscore. The data organization in the data schema is based on the molecular hierarchy I described earlier. So there are core objects that correspond to the different levels of the molecular hierarchy: entry, entity instance, assembly, and chemical component. The schema is powered by the JSON schema language, which means that the specifications are in JSON, and the information that you retrieve is in JSON format, which is one of the most common data exchange formats these days. So how is PDBx mmCIF data expressed in JSON format? If you look at JSON, it's just generically a key value pair. And PDBx mmCIF, although maybe you might have seen it as data in tables, PDBx and mmCIF data also can be expressed as key value pairs, as shown here. I'm just showing a couple of examples about experimental method and maybe the title of the structure, and that information can now be expressed in JSON format, which is how it is stored in our data API. The RCSB extension part of the data schema has some common data objects that I would like to highlight. Specifically, the positional features. These are available for entities and instances. And for example, these could be from cath, scop, or features that are integrated from external resources, or it could also be positional features that are from the PDB data itself, like ligand binding sites or mutations. We also have positional feature summaries that will provide some statistics about these features. And there is the annotation object, again, mapped at the entity and instance level, for example, like Go annotations, Interpro, or PFAM annotations. So these are common features or common data objects that you will find in the schema that can apply to multiple core object types, but we follow kind of the same logic. In addition, there's also provenance information to distinguish between what data comes from where. If it is something that's coming from PDB or derived from the PDB, then the provenance is PDB. If not, from whatever external resource the data is derived from. I want to finally show some examples here. I've chosen 3 different examples to cover the different aspects that I went over. So here, all these are in the data fetched from the data API, all in JSON format. We have information at the entry level, polymeric entity level, instance level, and at the assembly level. There are identifiers that uniquely and unambiguously identify each of these objects. And the specification for these identifiers is that at the entry level, it's just the entry identifier. At the polymeric entity level, it's the entry identifier underscore the entity identifier. At the instance level, it's the entry identifier dot the chain ID from the PDB. And at the assembly level, it's the entry identifier hyphen the assembly identifier. And you can, again, I wanted to highlight that the data can come directly from what's in the PDBx mmCIF file, for example, experimental method information, or the data can come from annotations integrated from external resources. For example, at the polymeric entity level, these are annotations from PFAM and Go, and we also have the provenance source to clearly identify where that was obtained from. Here at the Polymer instance level, I wanted to show an example of positional features that are derived from the PDB. This example here shows the ligand binding site, heme binding site in hemoglobin. Sorry, just give me 1 second. Okay. Yeah, so the provenance here is the PDB, and the important part is these are positional features. So obviously they're mapped to the residue number in the sequence. It doesn't have to just be one residue. It could be a residue range so that you can map something to a domain or a residue range. And at the assembly level, again, this is information that that's coming from the PDB archive. I color-coded these based on the the different kinds of information that is presented. So this is information from the PDB archive about the assembly. And there can be also information that is derived from, not directly from the PDBx mmCIF file, but also something that can be derived from the data that's there. For example, maybe the number of interface residues that you can calculate. So this is like a broad overview of how the data is organized and how the data can be, what kind of data can be retrieved using our APIs. To summarize, RCSB.org is powered by APIs. The Search API provides programmatic access to all functionalities supported by RCSB.org Basic and Advanced Search. The Data API provides programmatic access to all static data delivered on RCSB.org. And these APIs are freely available to all users, and we hope that this webinar would help you understand how to programmatically access these APIs and use them in your research. The APIs are supported by the underlying data schema, which provide information from the PDB archive obtained in the PDBx mmCIF, obtained from the PDBx mmCIF file itself, or information integrated from external resources. The data is organized and mapped into the molecular hierarchy, the entry, the different levels that I discussed: entry, entity, entity instance, assembly, and chemical component. And the schema is powered by the JSON schema language. The specifications are in JSON, and all output are in JSON format. So I'm happy to answer any questions if there are any. Before we move on to the next talk, we will have sessions on specifically on the data API and search APIs.
The one question that just came up is, how can you figure out which values are controlled vocabulary and which are free text? So how does the schema explain that to you?
So the schema language allows you to define what are the control vocabularies, and Jose in his talk will go to give you a demo of the schema browser, where you can browse through and find the different data objects, and some of them have control vocabulary terms, and you can find that from the schema. It's defined in the specifications.
Just very quickly, so one important thing is that we are basing our schema definitions on the JSON schema specification, which has a standard vocabulary. Defining enumerated values as part of this vocabulary. So we are just using that vehicle to kind of document the validation constraints. So if you will explore JSON schema specification, you will find the enum keyword that will list the possible values that can be associated with a given attribute.
Thanks, Yana.
Yeah, thank you both. And another more generic question is, can you give some background on mmCIF itself as a format? So there's no specific question, I guess, but what's the gist of how data is organized, maybe in contrast to a PDB file, or maybe what are advantages of mmCIF over the PDB format?
Okay, let me, at some point I had was a hidden slide. Maybe I will just quickly share my screen to go to that. Just 1 second. Okay. Do you see my screen?
Yes.
Okay. So this is an example. I have all these Zoom windows that block my view of the presentation. So this is example of the schema in mmCIF and the same schema in JSON. So there are specific, the dictionary definition language or the schema language has terms to define what is mandatory, what control vocabularies are, in the same way it can be translated into JSON. So that's just to support what Yana said. And to answer the next question about what are the advantages of PDB to mmCIF. So the PDB format, although has been there for a long time and has a lot of software support and it's very useful, has a lot of limitations. With growing data, it's and when you have large assemblies, especially with more number of atoms and chains, the fixed width PDB format cannot support large structures. And the mmCIF format is much more flexible. As I told you, it's just key value pair. There is no strict column width, or it's not implicit. The definitions are not implicit. They're explicit. You're saying exactly this is the key, that's the value, and that makes it easier to provide software support and can support all evolving methods. It's extensible and can handle the growing volume and growing types of data that's coming in. Does that answer the question?
I would hope so. So there are still a number of other questions, and we will answer them in the document in the next couple of minutes. But for the sake of time, it's probably best to move on. But if you have any remaining questions,
if there are other questions, I will go through the Google Doc and answer them.
So yeah, totally feel free to continue asking questions, even for previous sections, and we'll try to answer them still. So
yeah, please do post your questions. We will review and keep answering them on the Google Doc. Okay, over to you, Jose.
All right, thank you, Brenda. All right, let me share the screen. Okay, so in this session, we're going to be talking about data APIs. So one of the two APIs that sort of the two important APIs, the most important APIs behind RCSB.org. And this one is the one sort of closest to the schema. This is how you can get data from as it is stored in our internal databases in the schema that Brenda has been presenting. So first of all, let's see, what is data API exactly? It is about retrieving data once you know the identifiers for the data. This is PDB identifiers, not only the main entry identifiers that you probably know already if you're familiar with PDB data, also the other layers, the other levels in the hierarchy, of the molecular hierarchy that the PDB represents, all these entity identifiers, assembly identifiers, etc. These identifiers that you supposedly know already, they are coming from what? From an external API, from another resource, another website, referencing papers, or you have your own pipeline where you somehow process PDB data and obtain identifiers out of it, and you want to then query for data for each of those. It happens a lot that you don't know the identifiers and you want to search for something specific, you have a specific problem to solve. And that's why the typical workflow, I would say, is first you would use the search API to express a certain search condition that will return identifiers to you. Let's say you're interested in human proteins that are homodimers. You would express that in some way in search API, and Jana will present that part in next session. And then that gives you identifiers back. And with those identifiers, you can go to a data API and say, well, now I want to get the resolution experimental method and any other notation for that's present in our databases. So that's what you would use data API for. That will be the normal workflow, and the examples I will present will be one of these sort of workflows. So the data API has two different interfaces. One is a traditional REST interface with endpoints per granularity. Here I show two examples of those endpoints. We have to get all the information for a certain entry. This is the endpoint in REST. To forget all the information for a certain assembly. This is the endpoint. And these give you all the data for that specific granularity level. So there's no filtering at all. You get everything out, everything that we have for it. So if there's many annotations integrated, you will get everything together. And then there's the other interface, GraphQL. GraphQL, in contrast to REST, is a single entry point where you can traverse the whole schema. This is how a very simple query looks like. You want to get an entry, and you want to get just experimental method of it. So you specify like this. And so the point of GraphQL is you will get the data that you need for your use case, and just that, and all in a single query. It's sort of, as you see here, a JSON-based query language. And for both of them, the output follows the schema that Brina has been presenting, and it's all in JSON format. And it is important to note that sort of the main part of the data is all in GraphQL, which is what I'm going to be focusing on from now on the rest of the talk. But there are some specialized endpoints that are only in REST. Holdings is one of the examples of this. So holdings, if you want to know all the identifiers that we store currently in this week, you go to the holdings REST endpoint. Okay, so for those new to GraphQL, I should say a few words what it is about. It stands for Graph Query Language, and for graph here means basically objects. So objects are graphs, and then the hierarchy of in object, where objects and sub-objects, they're connected by edges, and the nodes are the fields between these different parts of the object. This was introduced by Facebook, and it was released to the public in 2015, and it's been really a very popular, has been integrated by many resources, many of the big companies, and these days it's used by many open access resources like ours. So why did it why did it come up with it? It is because traditionally in REST you have the two problems that this would prevent, the GraphQL prevents, is the so-called underfetching and overfetching. So overfetching means that when you fetch data, like the REST endpoint I was showing in the last slide, you fetch too much data because you're interested, let's say you're interested only in the experimental method because you have a web application where you want to show just the experimental method for an entry. And when you use REST, like for instance, we have it in our implementation, you will get all the other data with it. So you are fetching too much. So that's overfetching. And underfetching means that you need to go through several requests to fetch all the data that you need for a certain application, which is not very efficient. So GraphQL is also solving that problem. You can then, in a single request, get all the data because you can go through the whole schema and get the parts that you need for your application. It is important to note that GraphQL, despite its name, is not a query language in the sense of expressing a search condition with it. What you express with GraphQL is, I want certain fields from a certain schema, and I want those. So this is an example up here. And you are basically with the same shape as the schema has, you express your the query in the sense of you express the fields that you want to get, and you're getting the output in the same shape as you're expressing it here. An important thing to know is that error handling in GraphQL is not quite like the error handling in REST, where you have HTTP response codes. In GraphQL, you get 200 response code for everything, and the errors come in the response payload in JSON format. So you have to go and parse the errors. This is one of the reasons why I recommend using a client that's already ready for you. GraphQL has become really a very big thing, and there's a very large ecosystem of tools in many languages. There are exploration tools, IDEs, visualization tools, editors, validators. There's automatic type generators where you can, for instance, you have sort of a larger project written in a strongly typed language. You can generate types directly from the GraphQL schema automatically. And most importantly, I want to mention that there's plenty of client implementations. I'm showing in a few languages, but there's really many. For all the popular languages, there are client implementations, and I really recommend that you should be using a client implementation, and our examples will be using Python with one of the more popular implementate clients in Python. Okay. So one of the tools, one of the tools is called a graphical tool. Notice the I between the graph and the QL. Graphical is sort of an IDE-like tool where you can build your query, your GraphQL query, and there's auto-completion, there's documentation as you type. You can browse the schema. There's a schema browser where you can search through it, or while you are in this builder, you can directly link to a certain part of the schema. And we actually offer this under this URL. And my best if I show it very quickly so that you get a feeling of how this works. I have here the very simple query I was showing before. You see already that there's a contextual search as I hover over things. And then when I start typing, I'm getting auto-completions on the different fields that apply at this particular level of the graph. And you get the documentation. There's the schema browser here, which usually would be showing like this. You have to open with the docs, and you can search. I can do something like search for resolution, and I get all the fields that contain that. Or I can simply browse it and drill down and go through the whole schema, and with all the documentation for each level. One other thing I can do is also I can type something here, like enter info, and I can control or command, if you're in Apple, control click, and you jump straight into this part of the schema, and then it gives you all the different available fields inside that one. So all these features, maybe you are familiar with them from, there's also, by the way, control space. Whenever you don't know what to type, you can get like, what's the different completions that apply here. So that's all features that you probably use from IDEs, and they're all available here in the graphical. So we recommend this as the main tool to explore the schema and to build your queries before you put them into your scripts. Okay. How do you submit a query? We have both get and post available for query submission. Here's the same example I'm showing until now, that very simple example. You put the payload after query as a get, but this has to be, of course, URL encoded, so it looks like this in real life. And in post, of course, it's a little bit more complicated, but yet again, I want to say we recommend using a client. Will take care of it. It will take care of the communication with the server, and especially important of the error handling. Otherwise, you have to get the you have to parse the errors also and understand what they mean. So the clients usually take care of that too. This slide Brenda showed in her presentation. Just want to have it as a reminder. We have the different levels in the molecular hierarchy of the PDB data. We have the different levels or granularities, entry corresponding to the asymmetric unit in crystallographic entries. In this case, we're showing the example of the hemoglobin, the human hemoglobin. We have entities that can be polymeric or non-polymeric. For polymeric ones, it represents unique molecular polymeric entities that have a unique sequence. For instance, in hemoglobin, there's alpha subunit and beta subunit. There's 2 of each in the entry. So the next level is that those 2 copies of the entity, which might have slightly different conformations in 3D. So this is the polymer entity instance or chain. And there's also non-polymer entity instances. Then there's the assembly, which is the quaternary structure or the biological assembly as it is in physiological conditions. And there's the chemical components, which are the components of the polymers or the one component of the non-polymers. And this is just simply the molecular definitions for for that specific component. And I want to again point to the identifiers for each of these levels. Brenda already presented this, but we have special conventions in our APIs to present the identifiers, underscores for entities, dots for chains, hyphens for assemblies, and we have the chemical component identifiers that we use as they are. By the way, there are 3-letter codes, but they will be soon be up to 5 letters, and that will happen sometime by the end of this year. And our APIs will start serving those. So then, given this hierarchy and these granularity levels, in GraphQL, we have 2 ways to get through that. From the top level, that's what you type at the top of your query in GraphQL, there's top-level accessors, and there's one accessor per granularity level. Then, for instance, there's entry or there's assembly. But then there's also 2 flavors within those, which is the single or the list. And important to note is that when you do a list and there's one of the identifiers as composed, we use the composed version of the identifiers, whilst if it's a single one, we have an explicit parameters for the different parts of the identifier. Then there's connection accessors from other granularity levels. So for instance, let's say I start my query from polymer entity instance, from chain. I express it with a chain identifier. I can then navigate the schema and connect to another part of it, in this case, a parent, the polymer entity, the parent of this polymer entity instance. And then I can ask for fields from that parent, and then I can do another jump and go to entry, which is the parent of polymer entity, and then also get something from that entry level. So this is, for instance, I can get experimental method, but I also can get data from this instance level and the entity level. Okay, with that, I'm going to show some examples. I think that will show much better, explain things much better. Okay, first of all, quite a simple example of you have a bunch of PDB identifiers, and you want to get very basic data like the structure, title, method, resolution, are worker free, and also I'm showing here resolution, another resolution field I want to explain now. So I go here, I click on play, I get the results on this side. I can fold this in, and you see, first of all, that you have an array of entries because it's a list where we're provided here. And then there's an object, and the object has exactly the same format as your input. So you get all the fields that you wanted. And it can happen that a certain field is not available for some reason. For instance, because this is an old PDB entry, it doesn't have the annotation of our work and are free. So this will come as null. And then It can happen also that, let's say, this last identifier is electron microscopy entry, and it doesn't have a refined field at all. So that whole thing is null. So that can happen at any point for any optional fields. And then I want to also I wanted to introduce this field because it's something, one of these extensions. They are in the RCSB extension of the mmCIF schema that we have, and it's an extension that where we provide some useful information for at the entry level, and one of them is resolution combined. If you want to grab resolution for different experimental methods, you will have to grab it from this field for crystallography, from another field in electron microscopy. Here we have this as a convenient field that you can get the resolution in a single place. So that can be convenient. So that's one example of how we use the extended RCSB schema. All right, so going to another example. This time I start a polymer entity level. I provide a few polymer entity identifiers with an underscore. And then I want to get source organism, taxonomy ID, scientific name. And I want to get also information on the groups, which is a feature that we have in our schema, where we basically group entries or some of the granularity levels. In this case, at the polymer entity level, we group them by similarities. So for instance, we can do it by sequence identity clustering, and we have a certain threshold for that, and we have a group identifier for that group. This is can be very useful for deal with redundancy, and there's some more tools in Search API to also do queries that take grouping into account, but you can also use it here because you can ask for the group identifiers, and this will be consistent across the whole data and within a given week. Okay, so another example, annotations at the chain level. So in this case, I'm starting with polymer entity instances of chains. So I have chain identifiers here, and I ask for annotation. This is one of these common data structures that we use across the schema. In this case, it refers to chains, and it's this kind of annotations refer to the whole chain. There are features, data structures that refer to positions in the chain or in the entity. So for instance, with this one, you get everything that we have as annotation in polymer entity instance for this entity, which happens to be cath, scope, scope2, and ECOD. This will also appear, these particular types of annotations, cath, scope, and so on, will appear also as positional annotations, as features, but they're also available at the annotation level so that you can grab all the annotations for a certain chain. All right, so just want to show also that we have data, we have integrated, as we showed in our crash course about computer structure models, we have integrated 1 million computer structure models from AlphaFold model archive, and the data is also integrated, and that the model CIF schema that they use is integrated into our RCSB extension. And you can get things like for any of the AlphaFold models that we have integrated, you can get the global PLDT value, for instance. And last example, a bit more data, and this is data, the sort of added value data we calculate in RCSB that's not in the mmCIF files directly. We can get an assembly. So I started with assembly level here. This is the tetramer from hemoglobin, human hemoglobin. I can dig into interfaces and ask for information for each interface, like interface area, number of interface residues. And I can also get information for each of the partners of the interface, or the two partners, and then features. So this is using the feature common data structure. So this is an example. So you see the interface area, you see the number of interface residues, and then features. The features we have, for example, are the accessible surface area that can be for the unbound molecule or for the bound molecule. So that's it for all the examples. Then I had 3 questions that sort of come up quite a lot. I just want to briefly answer them. I've sort of answered this first one already, but I just want to comment on this again. And I realized I didn't go through this slide. I don't know what happened there. And then there's opportunity to go back to the slide. So how do I find what field has the data that I want? We have, you can do query by example in RCSB author. So let me show that slide because I sort of jumped through it. We have a data API button in a few places in the RCSB author website, in structure summary pages and in ligand summary pages. And this will get you the data that the GraphQL query is needed to get the data for the rendering that you're seeing for the page. So I'll show you that. I think this can be quite useful. So if I go to RCSB.org and I go to random entry, I see the structure summary page, and you see the button here. And if I click on it, I get the graphical application with the query, and I can run it, and you get all that data. That's the data that you're seeing rendered all over this page. Another example is experiment. I can do the same. There's data API button. So all the data which is specific about the experiment here, I can go here, I get all that data. So this is a way to get an example of all the fields that are relevant for experiment, for instance. And I want to also, in this case, it's interesting to see how, again, we have, if you're familiar with the mmCIF schema, all these fields happen to be really directly out of the mmCIF schema. So there's no RCSB extensions here. So if you're familiar with the dictionary from mmCIF dictionary, you already know a lot of the fields that you need to work with. Yeah, okay. So with that, the other, then the schema browser that I was showing in GraphQL is also a way to find the data fields you're interested in. Another question that comes often is, can you do filtering and from the request? Can I show in the request say that I want to get annotations of type scope only? That's not possible as we have implemented it right now. So the filtering has to be done by the consumer. And another common question is, how do I get data for the whole archive? So for that, you need to go to the holdings REST endpoint and then do GraphQL queries by batches. We recommend doing batches for efficiency, something like 1,000 identifiers at a time, and then you can go through the whole archive with that. Okay, so that's it. These resources are also in the Google Doc, and so that's all I wanted to say for now. Just happy to answer any questions. So I show the Google Doc in case there's.
Yeah, thank you. Like one question that came up twice, I think, is about chain identifiers. And let me find the question. But basically, there's this difference between author assigned chain identifiers and programmatically assigned chain identifiers of ASM-ID and label ASM-ID. And the question was, like, what do we use in APIs and how to make sense of both of those pieces of information?
Yeah, that's a very important question, very important detail. We are using consistently through the APIs the data items that were introduced with the mmCIF dictionary. So the label ASM-ID, so not the author chain ID, but the mmCIF one that starts from A sequentially through the alphabet. That is for chain identifiers, but also for residue identifiers, where there are two kinds of residue identifiers. Also, the author provide the ones with insertion codes and the sequential ones that were introduced with the mmCIF schema. We are using the sequential ones from the mmCIF schema. There are ways to translate in the, you can do a GraphQL query to get a translation, but all the endpoints, all the connections, all the referencing happens through the main identifiers. The label ASM-IDs for chains, the residue identifiers in the mmCIF schema for residues. So that's the convention.
Thank you. Another question is for NMR structures. Can I fetch only one out of many solutions. So I would say this refers to, can you retrieve data from data API for models that aren't the representative model?
Well, we don't really, in this schema, we don't store coordinates. That has to be clear. So that's something maybe I didn't mention. Yeah. So these models are basically conformations. So really is, as it is now, models should be homogeneous. So they're purely different coordinates with the same content. So we don't have really more information about specific about models in our data.
Maybe expanding on that, there, for example, secondary structure annotations, and we only provide them for the first model. So even like everything that is derived from the coordinates, we only provide information from whatever was the first model. So NMR support is somewhat limited, I would say, as a caveat of our APIs.
Mm-hmm.
Another question was, what happens if an old entry doesn't have assembly information?
And that is, I believe it doesn't happen anymore. And that's been remediated. So there are assemblies for all entries. And if there's someone in here from the migration team, may want to correct me, but I believe that was corrected in some recent remediation. So that should not happen anymore. And to be clear, our APIs are keeping update with the main data that comes from the biocuration pipeline. So we are up to date with all the whatever data was remediated and all the work that's done in the remediation side of things.
So maybe a couple of short questions for the remaining minute. Another one is, do chemical components have instance identifiers? I presume this talks about ligands or things that are explicitly not part of a chain.
Yeah, I'm not sure if the question is, so there's two things to distinguish, right? One is non-polymeric entities, which is what is a molecular entity in a given PDB entry. And then there's the description of the components of those non-polymer, which in case of non-polymeric entities, it's a one component only. The description of that one component is the chemical component. And so there's a distinction also in our APIs of non-polymeric entities, non-polymeric entity instances. In this case, for instance, there's 4 heme molecules in this assembly. Those are non-polymeric entities and instances. And there's the chemical description of it, so which is sort of just, what's general about a chemical entity. Not sure if that's answering the question.
I think this is a great post to go on break. We are going to come back in 10 minutes. So let's get started. And thanks everyone who stayed on with us. And welcome to the next session of our crash course. My name is Jana Rose. I have a background in structural bioinformatics, and I'm a scientific software developer at RCSB PDB based at UCSD in San Diego, California. So welcome everyone once again. In this part, we're gonna talk about anything you might need to get started with our search API. We're gonna first talk about the basics concepts, then we will look into how to write search queries and consume an API response. And I hope you all can hear me well, but if you can't, please let us know in the chat and I'll try to adjust. All right. One of the hardest parts of working with data is making sure that you have all the right data sets that you want to work with. Navigating through vast amounts of biological data can be very challenging. Today, I would like to introduce our Search API, which is a very powerful tool for querying the RCSB PDB data. And Search API provides an interface for applications to perform search operations by sending and receiving data using the REST endpoints. There is a custom language that defines and expresses complex queries. And both query and results are sent as JSON objects over the HTTP protocol. First, let's start with the overview of the different type of search options that are exposed through our Search API. The most basic search option is text search. Text search works by matching specific keywords and values associated with a structure. For example, you might want to find all the structure deposited during the pandemics, or you might want to find all the structures solved with experimental method being X-ray diffraction. This is a great tool for performing general purpose searches where you're looking for specific information. We also offer a number of scientific search services. Think of a scientific search as a type of search where instead of searching for general information, you use specialized tools for detecting a degree of similarity in scientific data set. These search tools are often used in fields such as bioinformatics and cheminformatics and aim at finding data that are structurally or functionally similar to your query. For example, structure search allows for finding molecules with similar 3D shapes. And this is a critical task to understand the function of micromolecules or studying interactions between them. Sequence similarity search is fundamental in bioinformatics. You can search for DNA, RNA, or protein sequences that share statistically significant overall similarity, which may reflect common ancestry in case of homologous, for example. Sequence motif search is another example. Sequence motifs are short patterns of amino acids or nucleotides that have biological meaning. They typically have constant size and are located within a certain distance from each other. They are also often repeated and conserved in functionally related groups of sequences, and they can help to detect those functional similarities when overall sequence similarity is low. Sorry about that. However, in some cases, it can be hard to detect functional motifs based on sequence data alone. Then structure motif search is very useful for finding conserved and recurring three-dimensional arrangements of residues. For example, catalytic sites play a key role in enzymes and often have a well-defined geometry to enable interactions with specific substrates. Last but not least, the chemical search finds small molecules with structures or chemical properties similar to reference compound. In pharmaceutical research, scientists search for molecules similar to known drugs, for example, to identify potential new drug candidates. And as you can see, the Search API can be leveraged for a wide range of use cases. And most importantly, all those options can be accessed in one unified interface and combined in a single query that delivers most relevant results for you. So when you interact with Search API, you will be getting back the list of PDB identifiers that matches the complex criteria you have expressed in your query. So let's take a look at the query language, or in simple words, how can you express those complex conditions. Search API offers a full domain-specific language based on JSON to define queries. One important part of it is a query context. And query context consists of two types of clauses: terminal nodes and group nodes. Terminal nodes represent the individual search operations. Those are the basic building blocks in a search query. It can be text search or a sequence search or a structure-motif search. Group clause queries, they wrap around other terminal or group nodes, and they control the logical relationship between terminal nodes in search query. So you can include any number of terminal or other group nodes within a logical block defined as a by a query node. Another very important feature of the Search API language is the return type parameter. It allows you to specify the type of the identifiers you want the API to return back. You already heard about macromolecular similarity and how it's relevant to PDB data. So selecting appropriate return type is relevant for scenarios when you are searching for properties that are specific to a level of a macromolecular hierarchy, and you want the results to be specific as well. For example, adult hemoglobin is composed of 2 alpha and 2 beta subunits. If you're interested in alpha subunits only, you want the API to return the first entity as not the second, because the first entity is mapped to the alpha subunit and the second entity is representing the beta subunit. Note that instance identifiers correspond to the label ASIM ID as it's defined in mmCIF schema. So this identifier is assigned by the PDB. It is different from author ASIM ID, which is selected by the author at the deposition time. This is especially relevant if you're used to working with PDB format, and oftentimes you would assume this is an author letter, but they can differ. So author label ASIM ID and author ASIM ID can be the same letters, but they can also be different ones. So beware of that aspect. Request options. Let's talk about request options. So this context allows you to further customize search results to better suit the needs of developers or applications that consumes the search results response. Common use case of or scenarios where those options might be useful are listed here. For example, you heard that we've integrated computer structure models and we're serving them alongside the experimental structures. So by default, the search will include identifiers for structures determined experimentally only. You can include the matching computer structure models with result content type parameter. Pagination parameter controls which subset of matching hits you want to retrieve, making it easier to navigate and explore large result sets. However, should you want to return all hit at once, you can replace pagination with the return all hits parameter set to true, and you'll get all the matching results in a single payload. Result verbosity is another parameter that controls how much additional information associated with a search hit should be included in the API response. By default, relevancy scores are returned together with identifiers, but if you don't need it, you can minimize the amount of data transferred by setting the result verbosity parameter to compact, and you'll get a simple list of IDs back. Redundancy filtering is a common technique used in the field of computational biology and bioinformatics to collapse, duplicate, or highly similar data, which allows you to which can you control with the group by parameter, and we have a number of relevant aggregation methods that can be applied to our data to retrieve unique or deduplicated results back. Finally, sorting involves rearranging results. By default, the results are ordered based on relevancy score from best to worst. You can choose, for example, to change it to newly released structures to come first by using an attribute name in a sort by parameter. So as you can see, the query language is quite complex. So how can you learn everything about it? Well, Search API is documented with the Open API specification. Open API defines a standard language agnostic interface to HTTP APIs, which allows both humans and computers to discover and understand the capabilities of the web service. Here you can see a snippet from the Open API from the Search API schema. You can download it following this URL. You can also explore it through the UI, and now we are gonna switch to it because I really would like you to see it in action of how this reference documentation can be useful to understand how to write queries in Search API. So this is a UI tool that reads the specification and displays it for you. You can see all the available services. You can see on the right the endpoints, and the request and response structure is described in a central part of the screen. So let's go to the search service, which we're interested in. We support both get and post HTTP methods for Search API. So if you navigate to one of them, you will see basically on the right side what's the endpoint you should be hitting. Some examples that are generated roughly from the schema as well, but don't pay too much attention to them. However, what you want to be focusing on is, first of all, is a definition of the query object. So we have, in the case of the GET request, you have a JSON parameter, and this is how you need to structure it. For example, we're talking about query context. Here is how you define it. We saw that group nodes and terminal nodes can be used to build complex queries. And this is the structure of a JSON object that will express your search intent. So you will have a type here, and this is basically the name of a parameter. And on the left and on the right, you will have a type of this parameter, any constraints on what values this parameter may contain, and you also have the description. So let's, as an example, go to the terminal node, and let's say you want to write a structure query. So you want to perform a structure similarity search via API. So what you need to define is the terminal node with parameters. And here you can explore in the structure query parameters tab, you can explore how the query should look like for that. You see value. Value is how you defined your target structure. And there are a few ways you can do this. You can specify structures that already exists in RCSB PDB, being it a chain or an assembly. Note that, again, this identifier is this label chain ID. All our APIs done in the same way with respect to how we treat chain identifiers. So it's always label ASIM ID. But you may also upload a custom file, or if you host files somewhere, as long as it's matching one of the allowed formats, you can paste a URL to that file with coordinates and execute a search API query on the custom, coordinates that isn't available in RCSB PDB. Another important thing that you, as a developer, want to look at here is responses. This is the list of responses that you can potentially get from the API. For example, if you're writing a query and it doesn't adhere to the constraints defined in the request schema, you will get an 400 response back, bad request. This means you will need to take a closer look of how you define a query and make sure that the schema is respected. And another important aspect is that you will have a 204 whenever search result doesn't return anything, as opposed to 200, everything is okay. You have your payload, it's not empty. You can go ahead and process it. And here below you find a response object specification, meaning that your application can expect data being in this format. Again, you have a bunch of required or optional fields, and you will get result set, again, depending on which verbosity option you specify. It can be either just list of strings or a more complex object. And all this information you can find in this reference documentation. So it's very, very helpful for developers to explore how to use APIs to write queries. So let's go back to the presentation. All right, so you might be asking yourself, oh, okay, so now I know how to write queries, but if I want to perform text search, how do I know what attributes I can query? And we have developed a number of resources to assist you in discovering the attributes available for search. We expose an endpoint with schema. So as Brenda explained earlier, we have a very strongly defined schema for our data, and we make it publicly available as well. So you may hit it and be informed based on that. We also have a comprehensive documentation in our tutorial with the page that allows you to filter the attribute by name. On that page, you'll find the exact attribute name you should be using, the list of available operations that is applicable, the type, the description, and finally our RCSB.org Search UI is a great source for suggestions of what attributes are available. So you can go to the advanced search and take a look at the menu. Anything that you see there is also available through the APIs. Another excellent source for learning how to write queries is our structure summary pages. You can find search links placed in various places. For example, I'm looking at the macromolecule snippet on structure summary page. And here you immediately can find links to perform sequence search, the structure search, the text search. So when you navigate or use one of those links, you will be exposed to the advanced search interface from which you can go to the query editor by clicking the Search API button on the right upper part of the screen. And in the Search API query editor, you will see a practical example to follow. You can change your query, and let's say you're not interested in a Homo sapiens, but in a mouse. So you can update the value and run the query just to explore how the change in the query will change your results. And we have also developed a bunch of resources that are useful when you want to learn about Search API. So we have seen reference documentation. You can find all the relevant links in the user guide that you can find at search.rcsb.org. There is a tutorial page on our educational PDB 101 resource. And should you have any questions, please don't hesitate to hit our help desk. It's very helpful. We are happy to help you if you have trouble to understanding how to write a specific query, or if you have any questions about our services, please feel free to hit the help desk. And again, just to reiterate what other panelists mentioned, a Search API is used to power our RCSB.org website. So it's a real world example of how this API can be used to build a complex application. So surely if you need a search functionality for your application, you can follow that pattern and build a very, very complex application based on our Search API. You can also use it in your pipelines that are tailored for bioinformatic analysis as well. So that concludes my part, and I'm happy to take on a few questions if we have any. Let me.
Thank you, Jana. Yeah, we don't have any questions in the Search API section at this moment. So if you have anything and we missed it, make sure to add it to the appropriate section so it's easier for us to see it. And already some coming in. But like maybe one remaining question more relating to data API. There are two questions on tabular reports, basically. One from Pierre, who asks, can we get all the information in tabular report by using GraphQL API? And a related question by Omkar is, on the website, I can search, I can get the search output in the table format, even if the data is nested. Is there information available on how the table is generated from the JSON output of data API? And I think both of them are interesting questions to explore.
Sure. Great questions, by the way. Jose, would you like to answer them, or should I?
Go ahead. I mean.
Okay, so then let's start with the first question. Can you please repeat it once again, Sebastian?
It was, can we get all the information in tabular report by using GraphQL API?
Yes, any information that is available in tabular report is also available in GraphQL API, and even more. Our APIs include more information that you can explore through our website. And yeah, does this answer?
I think it also kind of relates to this second question that, you know, the table format is available if data is nested at data API level. But maybe a point to make is that we basically urge all users to use the API directly and not to use tabular reports, because as stated, it's not easy to convert from the representation that data API offers, where you can have those complex tree structures and like define a hierarchy that isn't easily represented in tabular form. So it's always better, at least in my book, to use data API directly if you want to pull information on anything that is a nested property. That's way more powerful and way more convenient, I would also say. And as Jana mentioned, there's a whole lot more information available directly via data API that is not accessible in tabular reports.
Yes, that's a great layer to that. Another point I would like to make is, as you see, our data is hierarchical, and data API responses are structured around that aspect. They also can be deeply nested. In some cases, you will have more than 2 levels of depth in that response, which is probably the way you want to consume the data when it comes to consuming the naturally hierarchical data. It also helps to have no ambiguity with respect to relationships between data items that belong to different levels. So yeah, using data API will unlock a much more powerful way for you to interact with our data.
Right, thank you. Search API specific question is, how are these scores calculated? And yeah, that's all the information. So it differs between services, but yeah, maybe you can answer it on a general level.
Yeah, so scores, it's a very complex and broad topic in general. I will really try to boil it down to few things. So first of all, every search option that we have described has own way to calculate relevancy. And what we are, so basically, if in example of text search, the score is calculated by the engine that we use behind, which is Elasticsearch engine, and we just use their algorithms to define the relevancy. So it really depends. To answer a specific question of how the score is calculated, it really depends on whether you're interested in knowing how the structure search score is calculated or a sequence search, because those will be different, fundamentally different algorithms. And then there will be a step of normalization and aggregations of scores. So if you do write query that involves multiple search options, you will get back a score that represents an aggregated values based on all options included. And in fact, you can have a very detailed metadata on scores in the API response as well, if you have a very complex query. And you also can get raw scores before normalization. So again, feel free to explore that, and feel free to hit us with specific questions if you have after the
Thank
session.
you for your answer. So I think like one last question that is pressing, I would say, is there any email, RSS, or atom feed to basically stay informed about changes happening to our APIs?
What a great question. We would love you all to subscribe to our mailing lists. Let me see if I can pull them on the screen. I think it's API@rcsb.org, right? From the memory, I get it.
Correct. API@rcsb.org.
API@rcsb.org. We also send announcements to PDBL and CCP4 mailing lists. So if you are on one of those already, you might be seeing sometimes emails from us. But if you want to stay tuned, please subscribe to yet another mailing list, and you'll be in always up to date.
Right, thank you. Yeah, we'll update the document with helpful resources. And for the sake of time, let's move on to Dennis's section on Search and Data API, the hands-on teaser.
Thank you, Sebastian.
Thank you, everybody. Let me share my screen. I'm assuming everybody can see this. Just to confirm people can, right? Okay, if you can't, let me know.
Yes, we can.
Thank you. So welcome everybody to the last session of today's crash course. I'm Dennis Peel. I'm a scientific software developer at the RCSB PDB based out of our Rutgers University data site. And for this session, I'll be walking through a quick demonstration of a pipeline that combines the use of the Search API with our Data API, and using a specific example case. So for this example, let's imagine that we're interested in all the structures of insulin, and specifically we're interested in getting all the citation information for those structures. Well, how do we go about doing that? Well, it's a pretty simple two-step strategy. The first part of this is to use our Search API to search for all the structures of the protein insulin. That'll then return a list of all the structure IDs that match that query. We would then take that input list, and we would take that list and provide it as input to our Data API in order to fetch the citation data for each of those entries. And then that would provide us with our final output. So like I said, it's pretty simple two-step strategy where you get to use your Search API and then the Data API. And now I'd like to walk us through like a live demo of this so that you can get an idea of how you do this. And I'm going to go about this process assuming that I'm new to using our APIs. So let's first start by going to rcsb.org. And rather than trying to create a new Search API query from scratch, let's start from a boilerplate, because it always makes things easier. So we can do that by just performing any search up here, and let's just search for insulin. And we'll click on insulin here under uniprot molecule name. So this performs an attribute search, which returns all the structures of insulin, which have a uniprot molecule name of insulin. And we can get the Search API boilerplate query by clicking on this button up here. So if we click on this, it'll open up our Search API query editor. And if we were to hit the run button, we would get the same list of results that we just saw. Of course, this is truncated. This is just showing the first 25 rows. If we wanted to look at all the rows, we could increase this number. And you can also paginate the results if you prefer, which is a very programmatically friendly way of accessing our APIs. So you'll see that this, in addition to returning the identifiers, it also returns the scores. And in this case, the scores, and this relates to the question that was just asked in Jana's session, The scores are all 1 here because this is an attribute search, which is basically a true or false search. It either matches the attribute or it doesn't. But for the purposes of this tutorial, we don't need the scores. We're only interested in the identifiers. So let's clean up this result set a little bit. And we can do that by adding this additional request option of results verbosity. And so if we type in results, we see results verbosity appears. And then we're going to change this to be compact. By default, it's set to minimal. And if you're wondering how I knew this existed, well, it's in addition to preparing for this tutorial, all this information is provided on the schema that Jana presented just earlier. So if you were to click on this help button here, this would navigate you to our schema documentation, and you can explore to see what options are available and what are the possible values for that. So now when we run this, we get a really clean set of results, which is the list of IDs. And this is exactly what we need for providing as input to our data API. So I'm going to go ahead and copy that onto my clipboard. And now let's go to our data API. And again, instead of starting from scratch, let's start from a boilerplate. And we can do that by going back to the search results page and clicking on any of these structures here. And let's just click on this one. And in the corner here, as Jose pointed out earlier, we have this button called the Data API button. And this will, if you were to click on this, it'll show you the query that's used to generate all the data that's displayed on this page. And this includes the citation information that's provided here. So let's go ahead and click on that. And now we see the Data API query, which is in the graphical interface. And if we were to run this, it would provide us with all the data that we just saw on the structure summary page itself. And it's only doing this for specifically this structure. So first of all, we're only interested in the citation information. We don't need everything else. So we can basically just clean this up and remove everything that's not related to the citation. So I'm just going to highlight and delete these lines. And then I'm going to delete everything else after this. And of course, if you're interested in something other than the citation information, you're welcome to explore those other attributes and choose whichever one is of interest to you. But for here, we're interested in the citation. So if I hit run again, now we get only citation information for structure 1A7F. But again, we have a whole list of structures that we want to perform this query for. So how do we do that? Well, we can do that using this query variable down here and by adjusting how we're providing input up here. So down here, we're specifying a variable called ID, which is being fed into this variable up here. But we need to do this for multiple entries. So we can figure out how to format this by clicking on the query root node in the documentation explorer. We scroll down and we'll see here you have the option for performing it for a single entry, or you can perform it for multiple entries. And so we just need to follow this format in editing this query. So I'm going to basically just copy that and I'm going to change it to be entries. This has to be entry IDs. And then again, instead of just providing a string, we're providing a list of strings. So I have to change this to be in brackets and then put another exclamation mark there. And for sanity's sake, let's change this to be IDs. It doesn't really matter what the variable name is, but we're providing a list of IDs, so let's change that to be plural. And now all we have to do is just replace this with our list of IDs that we got from here. So copy that again, just to make sure, and I'm going to paste it right here. So now when I run this, now we get all the citation information for all the structures that we just queried. So we have 1A7F, and then we also have 1AI0, and so forth. So voila, this is a really simple pipeline for how to combine the search API and the data API. And again, the links for these queries are both provided in the Google document. So if you're looking at that, feel free to click on those links if you want to have the pre-generated query. And I just really want to point out that these query builders are really useful for exploring how to build your query and how to learn about our schema and the available data types that are there, or the data attributes that are there. So we always encourage you to start from a boilerplate like I just did. If you're kind of new to using our APIs and you don't know exactly what attribute you're looking for, chances are you'll be able to figure out by looking at these examples provided here. So let me jump back to my presentation. And so once you have that query that you've just prepared, you can then use many other tools for accessing our API and for running that request. So you can use command line tools such as curl to perform get or post requests. And you can also use your favorite programming language. So Python, for example, has a requests module that you can use to perform any type of request to our APIs. And there's also a GraphQL module that lets you perform GraphQL queries to our data API endpoint. Additionally, we're excited to announce a new RCSB PDB maintained Python package for accessing our search API, all via a Pythonic syntax. And the documentation for that is provided at this link here, which is again also on the Google document that we're sharing. So this package allows you to perform all the same types of search queries that you would be able to perform from the advanced search query builder window. And this is all through a Python interface. You can install the package using PyPy, and you can also follow along on the code on GitHub. And we strongly encourage you to take a look at the documentation, because there we have this quick start tutorial, which provides a pretty thorough walkthrough of how to use the package and provides a lot of examples for using it. And you'll be able to perform, like I said, basically all the same types of queries that you can do directly from our advanced search builder, but you can do it from a Python script that you're working on. So with that, that concludes the part 1 of our virtual crash course on our APIs. Part 2 will be held at 2 different times. One will be next week on October 19th, and then the next, it'll also be held a week after on October 27th or October 26th, depending on your time zone. And we're doing this intentionally to accommodate different time zones. So this second part will focus more on hands-on activities where you'll be able to work with us on a particular question or use case of your particular interest. And however, because of that, we have to limit space for this part 2. And we also have some other requirements for participation. The first is obviously the registration itself, and you'll be provided a link for the registration following today's event. Make sure you fill out the exit survey. This is all at the very end of the Google document. If you don't have the link, you should also be emailed the link as well. We also expect that you're familiar with some of the basics of Python. And you also need a Google account, because a lot of the examples that we'll be providing during part 2 will be on a Google Colab notebook. So you need a Google account to access that. And then, of course, bring your questions and your use cases that you wish to investigate. So to give you a quick teaser of one example that we'll demonstrate during part 2, which is that you'll be able to learn how to create a data set that you can use for training your own machine learning and AI models. This will be specifically focused on predicting protein-protein binding sites, in which you'll first search for heterodimer complexes, and then you'll be able to use the biological features and annotations from the data API to help filter your set and create a training and testing sets. You'll also learn how to explore, you'll also be able to explore how to map positional features onto these structures, such as the secondary structure and the binding site residues. And with that, I'd like to acknowledge the entire RCSB PDB team for all their contributions to every aspect of our data resource. And a particular note, I'd like to highlight the presenters today, which were Brenda Vallet, Jose Duarte, and Yana Rose, as well as Joan Seguro and Sebastian. Sebastian's on here as well, and he's been helping a lot with all of our questions. So I'd like to give a shout out to him. And last, we are always seeking highly motivated scientific software developers. So if you know any undergraduate or graduate students who might be interested in applying their skills here with the RCSB PDB, please send them our way or have them send their resumes over to us. So I'd like to thank you again for joining us today. We'd be happy to take any final questions if we have the time for it.
I don't see any at the moment, but if you still have questions, then feel free to add them to the document, and maybe also use the comment functionality so that we see a notification that something is still not answered to your full expectations. So yeah.
And also, please be on the lookout for emails about the recordings for this webinar. It should be sent out as soon as the recordings are available.
Yes, and I just wanted to also mention that I'm going to add an exit survey to the chat, and also the link to register for part 2. I'll email that to you as well, but I'll go ahead and add the exit survey. The exit survey will take you directly to the part 2 registration. And if you want to just register for part 2 without the exit survey, then you can click that link separately. Thank you so much.
Thank you, Shema. And I see one question in the chat about how basic is the basic Python needed for the next session. I would say pretty basic. You need to know the different objects, like what a list is, what a dictionary is, things of that nature. If you're familiar with programming in general, you should be fine. But and especially if you learn Python at all, you should generally be fine. But the majority of the part will be focused on how to use Python to access our APIs. So just if you have questions that are more Python oriented than are use case oriented, we might not have time to address all of those. That's all. It looks like there's a question. How do I obtain the FASTA sequence protein from PDB ID using data API? So
I posted the answer to that question in the Google Doc. You can get the sequence from the data API.
Okay. Thank you for doing that. So yes, take a look at the Google document. Brenda provided a nice answer. And the Google document will also be shared with everybody. Obviously, you have access to it. Okay, I think that concludes everything. Thank you, everybody, for attending.
We look forward to having you in the second part of this crash course. So if you haven't already, please register. We have a lot of awesome things to show still. So we'll see you later.